Hi, in this Shader Stories episode, we're going to look at visualizing the Mandelbrot set. At heart, I'm a nerdy mathematician, so this is something I've been wanting to do for ages. This tutorial is going to be split into multiple parts. However, this first episode will get you all the way to displaying this in grayscale like my example here. Let's get started. We can start with a standard Unity 2D project, which I've simply called Mandelbrot Visualization. Note here that I'm using the 2D template with the built-in render pipeline. This is important. The way I'm going to render the compute shader is just simpler here. It won't work with the universal render pipeline. We'll go ahead and add our compute shader straight away. Right-click, Create, Shader, Compute Shader. I've called this Mandelbrot. Let's take a quick look at the stock shader code. The pragma lines define all your kernels, which will have functions within the compute shader. You can see we start with one called CS_main. So first thing is to rename that to Mandelbrot, as that's what we're going to be doing. We do this both here in the kernel line and in the function. There aren't really any style guides or naming conventions in compute shaders, so I default to lowercase with underscores, which is called snake case, for everything except kernel names, which I leave capitalized. To this end, I'll just quickly rename result to result in both definition and use of the function, and you'll likely have your own code styles. You don't have to copy mine. So what is result? This is our read-write texture, which we can read data from and write data to. This is where we'll ultimately display our Mandelbrot image. For now, the shader comes with some default logic. So let's just get that rendering into Unity before adding the Mandelbrot code. Don't worry about what it does, you'll see soon enough. The last thing I'll mention is the numthreads881 attribute. This tells the compute shader the level of parallelism you are wanting it to do in one go on the GPU. So this will do an 8x8 grid in the XY plane in one go, so 64 calculations. Optimal parameters for this will depend on what you're computing and the hardware you're running on. I would not worry about this too much. The best way to find the optimal parameters is by benchmarking them and picking the best. But like I said, it will vary on different hardware, so I wouldn't worry about it for now. This default should suffice. Back in Unity, we need to create a C# script to take our compute shader and display it somewhere. So right-click, Create, MonoBehavior script. We'll call this shader display. For simplicity, we're going to directly display our compute shader output on the camera. Starting off very simply, first we need to get a reference to our compute shader. We have a private serialized field because we want to set it in the inspector, but there's no reason for it to be public, of type compute shader called compute shader. Then we need our private rendered texture. This is what we're going to pass in and out of the compute shader. We'll also add a private boolean called needs update, which we default to true. We're going to use this so we only need to call the compute shader when the parameters change in some way. This is so we don't call the Mandelbrot function every frame, as it can be expensive. You'll note that I've removed the default start and update methods. We'll not need these just yet. We'll start by creating a new function called updateRenderTexture, where we'll do just that. This takes in the width and height of the texture, which will be integers, and the first thing to do here is to create the render texture if needed. So if render texture is equal to null, i.e. it hasn't been created, then we create a new render texture using the new keyword, passing in the width and height that we want it, and the color depth. We'll just use the standard 24-bit color depth. That is 8-bit value for each of red, green, and blue. We need to set one property on the render texture, that is enable random write, which we set to true. This is because the compute shader operates in parallel. You'll need to be able to write to arbitrary points at any given time. If you remember in the compute shader, the comment tells you you need to do this. If you haven't seen this curly bracket syntax before, this is just shorthand for doing render texture.enable random write when initializing it, which will save you that extra typing. Then we can simply call render texture.create to create it. Now we need to tell the shader that this is the texture to use. So first we'll just create a helper variable, an int called kernel. We use computeshader.findKernel and pass in the name we gave it, which was Mandelbrot. You can also specify them by their 0 integer index, in which case this would be 0, but I find using the names clearer in the code. Using the compute shader's set texture method, the first parameter is the kernel we want, then the name of the variable, which was result, followed by the texture we want, which is render texture. Now we just want to run the compute shader to update the render texture. This is done with compute_shader.dispatch, passing in our kernel and how many threads we need in each dimension. The shader was defined as numthreads 881. So in order to execute enough workgroups on the GPU, we need width divided by 8 of them, because they do 8 each, and the same for height. The workgroup side for Z is just 1, as we're not doing anything special there. That's it for this function. All that's left is to call this when the camera renders. To do this, we can implement the private void OnRenderImage function. This is called after the camera is finished rendering to allow you to add any extra processing to the final image. This is why we use the built-in render pipeline rather than URP. In our case, we're just going to replace it with our own output. This takes two parameters, the source and destination, which are both render textures. Add an if statement that checks our needs update variable, which starts at true, remember. And if it does need an update, then we call the update render texture function we've just created, passing in the width and the height of the source image as the size we'll need our render texture to be. Then we can set the needs update to false as we've done the processing. That means until we tag that again, we don't need to call a compute shader, which we'll eventually do when we're navigating around the Mandelbrot visualization. At this point, our render texture has been updated. We just need to copy that into our destination using the Graphics.Blit function to copy our render texture to the destination output. Back in Unity, we can drag our shader display script onto the camera, then the Mandelbrot compute shader onto our script, and hit play and see what's going on. You can see that we've got some output, so we know it's working. This is just the image you get with the default shader code. So now it's time to get going with the Mandelbrot fractal. So what is the Mandelbrot set and how do we define it? It's very simply defined by the following quadratic recurrence relation. That's a very fancy maths way of saying that you update Z by taking the square of Z plus some other bits. In fact, it's super simple. We're just squaring Z and adding on C. There are no other terms. So what are Z and C, and how does this work? The first complication is that we're talking about values in the complex plane here. That is, these are complex numbers. So rather than just having something like Z equals 4, instead you have Z equals 4 plus 3i, or something like that, where the 4 is the real part and the 3 is the imaginary part, hence the I. But don't worry if you haven't come across complex numbers before, I'll give you enough context to get this working as we go through the shader code. So how do we apply this to get these cool Mandelbrot fractal images? That's why you're all here. So consider our 2D texture as just a 2D drawing. So instead of it being a plane with X along the horizontal and Y the vertical axis, we take the horizontal to be the real part of the complex number and the vertical to be the imaginary. That means for every pixel in the texture, we've got an XY coordinate, which we can map to a complex number. Now we have that complex number, we can keep applying our recurrence relation until our stopping condition is met. For a point to be considered in the standard Mandelbrot set, then the size of Z at iteration n must be less than or equal to 2. Formally, it's only there if it's less for all n, but we live in a finite world and I don't have that much compute power, so we'll just bound how many iterations we do before declaring whether it is in the set or not. When looping through, that means if ever the value is bigger than 2, we can stop and say it isn't in the set. All these cool pictures of the Mandelbrot set that you've seen aren't just in or out like this one. Instead, they often have gradients like this black and white one. What's happening here is rather than colouring as say white for the points that are not in and black for the ones that are, we interpolate between them, i.e. shades of grey, based on how many iterations we did before we determined that the point was not in the set. That's quite clear to see in this image here, where we've got just a limited number of iterations before stopping. That's enough basic explanation. Let's get stuck back into the shader code. Okay, so back in our shader code, we're going to implement the Mandelbrot function now. We'll worry about the parameters and getting the data into the shader in a moment. For now, we'll just create the function in isolation. For this function, we'll call Mandelbrot iterations. We're going to pass in our point and some limit of iterations, and return which iteration it was when we found out it wasn't in the set. So that means we're going to return a uint, an unsigned int. Unsigned means it's always positive. We pass our point c via two variables cReal and cImage for the real and imaginary parts. If you remember, the function we're computing is z equals z squared plus c. We need two doubles for z, which start at 0. Then we're going to do our iteration loop, which you can see the skeleton for here. At some point we'll break out of the loop, or the loop will finish and will return iter, which is what iteration we got up to. Before we dive into the loop contents, I'm going to add two extra variables. These are for the real and imaginary parts of z squared. These start at 0, as in the first iteration z is 0, so the squares are 2. The reason these are defined outside the loop is that we actually need the values twice. Once to do the z squared calculation in the formula, and once to check if we've met our threshold, so this will be an optimization. I debated whether or not to keep this in for this video. I hope you don't mind me indulging myself and keeping it in. It shouldn't make the code too much more complicated to follow. Okay, so in the loop we need to calculate z equals z squared plus c. For those of you who don't know complex multiplication, I've expanded it out here. You do it just like you would if you were doing algebra and imagined I was just some variable like x. The key in complex numbers is that I times I, or I squared, is -1. We can calculate the imaginary and real parts separately. We start with the imaginary. You can see this is 2 times z real times z imag. Real times imaginary is straightforward. Rather than doing 2 times, I just add it to itself. That's another GPU performance thing. Finally, I add on the imaginary part of c. Then for the real part, we take the difference in squares using our helper variables and add on the real part of c. To do our check, we need to know if the absolute value of z is less than or equal to 2. In complex numbers, the absolute value is the square root of the sum of the squares of the real and imaginary parts. Square roots are expensive, so instead we can just square both sides to remove it. This gives us the sum of squares is less than 4. So we can calculate those squares for the real and imaginary part. You'll notice these go into our squared variables, which means they contain the right values for next time we need to use them through the loop. We can then compare the sum of them. If it's greater than 4, we know it's not in the set. We can break out now rather than carrying on because the update function has a z squared term. So if it's not in the set now, it will never be in the set because it will keep getting bigger. Conditionals and breaks aren't generally great in compute shaders. This is probably not too bad in this case. Maybe we'll investigate later. As an aside, the reason this is bad in shader code is that all the threads have to execute the same instructions. Any one of them hasn't finished, all the other threads have to sit around waiting for the last one. That's it for the base function. Let's get that called from our kernel. First up, we're going to need some variables passed into the shader so it knows what part of the space it's drawing. Firstly, we need to know the size of the image in pixels. We'll see why in a moment. And then we'll need the reference point of the image. That is, what coordinates are the center point of the image. You have two choices here. You could use a corner or the center. I've chosen the center because that means when we implement zoom in a later episode, the reference point we're centered around won't change. Which brings me nicely on to the final variable, pixel size. The shader will operate on pixels, so we need to know how far each pixel is along the real and imaginary axis. Okay, so now we can update our Mandelbrot function. First thing we need to do is convert our pixel coordinates x and y into complex coordinates. We'll start by taking the ID, x for the real direction and y for the imaginary. This is an unsigned integer, so we'll cast it to a double. Here, 0, 0 is the corner of our image, but as we said earlier, we're operating around the center. So if we subtract half the width and height from the real and imaginary points respectively, this does that. So now we've got the real going from minus width over 2 to plus width over 2. The final thing to do is multiply these by our pixel size to get us into our complex coordinates for our offsets. Now we know what each pixel is relative to our central point, we can calculate the actual real and imaginary values. We do this by adding on the center point we stored in image real and image image. Probably should have given that an easier name to say. Now we have a point we can call our Mandelbrot iterations functions with. Here I've hard-coded the maximum number of iterations we can do into total iterations variable and set it to 32. In a later video, we'll get that passed in from Unity so we can modify it. Now we have our iterations for exclusion from the Mandelbrot set, we can set the pixels for this point. You could have white for not in the set and black for in the set, but often you see much prettier pictures than this. So what we'll do is make it a grayscale image. White will be the fewest iterations and black the most required. So we can calculate this by doing iterations for exclusion divided by total iteration. This would give us 0 to 1 value, which we can then use as our shade. This is the opposite way around, black to white, so we just invert it by doing 1 minus this value. we can now set the colour of the resultant pixel. If you didn't know, this is done as a float value between 0 and 1, rather than an integer between 0 and 255, which you may be used to. In the red, green and blue channels, we add our shade value. As they're all the same, that'll make it grey. And 1 in the alpha channel because we want it to be opaque. That's it for the shader. Back in our shader display script, we just need to pass in those extra parameters. So in our update render texture method, after we've set the render texture, we'll add in the others. Everything is a float, so we use the computeshader.setFloat command. First argument is the variable name, and the second the value to give to it. We add 2 calls for the width and height of the image, then 3 more for the real and imaginary part of the center of the image and the pixel size. For now, we'll hardcode the pixel size to 4 divided by the height. That will give you a full view of the Mandelbrot. Jumping back into Unity, we can hit play and see this in action. You can see our height of 4 is just right to see the initial big circle of exclusion at the first iteration. And even though we've only let it go up to 32 iterations, you can already see the Mandelbrot fractal pattern, which I think looks super cool. That's it for this episode. In the next episode, we'll implement the navigation so you can move around and explore the Mandelbrot fractal. As ever, the full code is on GitHub and linked in the description below. See you next time.